So in this part, we'll talk about getting Rssi values from a computer or a device. So Wi-Fi Rssi measurements are measured from received radio packets. The information can come from the configuration tools such as wireless tools or from dedicated features such as radio tap. With wireless tools, if you use the command iwlist with the interface name of your Wi-Fi card and the keyword scan, you get something like that here, and you see that you get, for instance, the ESSID of the cell here and its signal level here, the RSSI. The problem with wireless tools is that there is no native API to use it, only commands. So then you have solutions to use it with either a shell script, which is slow and hard to synchronize with another process, maybe with piping or writing into a file. But since it's a free software, you can download and read the code, modify it, and it's quite easy to understand with only several thousands of lines. However, it's only based on beacon and probe responses from the access points, so you cannot use it to get Rssi for any packet. On the other hand, you can enable the monitoring mode of a Wi-Fi card with a command or utility. This mode is especially known by Errata, which is a Wi-Fi encryption breaker. It is used to sniff any packet on the network, and for each packet, the wireless NIC gathers the various radio measurements. It writes a new header, which is called the radio tap header, and encapsulates the whole frame inside with this radio tap header. With radio tap, you have to enable the RFMon, radio frequency monitor, mode on the interface. For instance, with Errata, you can use the command rmon-ng start on your interface. Or you can use a traffic capture tool such as TCP dump or Wireshark. But how do you do from a software? It's quite simple. You can use libpcap, which is the packet capture library, and the iterator from the radio tap iterator library. And then you can analyze each packet, extract its relevant information for positioning, and use it in your system. For indoor positioning systems, what do you need as information? So you need the frame timestamp to know if your frame is relevant when you process it, the frame source address to know from which device it's originated, the frame destination address to know if it's the good packet you are processing, the frame from the device to the infrastructure, that's what you need, and the RSSI value, which is computed and included in the radio tap header. You may want to use other channel related values, but it's not mandatory. Then you need to use Pcap, packet capture, to capture the packets on the network interface card. You all know, I think, Pcap as you used it with Wireshark or TCP dump, and with Pcap you can read and write packets from and to the network. So how does it work? First you have to open a handle, you include the Pcap header, you have a pcap-t pointer called, for instance, my handle, buffer for the errors. you open Pcap Open Live on an interface with a buffer and some backlog. Then if you get something different from null, you can use the Pcap handle, else you have to handle the errors. How do you use the Pcap handle? You write a callback which gets some user data, your packet header pointer, which is the packet actually, and bytes, which is an optional field. So here you do something with the packet. Here you open and check the Pcap handle, and then with Pcap loop you use your handle, which is opened here, and the callback you define here. And when you end the Pcap loop, you clean up everything and quit the program. To stop the capture, you can, for instance, use a signal. So you include the C signal. You write a SIGINT handler, so you check if you get SIGINT, for instance, for the Ctrl-C shortcut. And if you get it and you have a handle, you can break the loop on my handle. So here you register the signal and its handler, you loop, and when you Ctrl-C on the keyboard, you will break the loop and clean up and go out of the program. What is the Pcap packet header structure? It's composed of three fields. The timestamp of the packet, which is a time val, so it has two members, the seconds and the microseconds, which is the date in which the packet was received. Then you have the number of bytes present and the complete size of the packet. And you can access the bytes with within the Kaplan limit, which is in the callback. So we are interested in i3 802.11 layer 2 header to extract MAC addresses, and then we'll use the radio tap header to get the Rssi. So in the MAC layer we have many fields, so we'll look at the addresses here, 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 and here, the frame control, these flags here to distribution system and from distribution system. So there are several Wi-Fi operating modes. In ad hoc mode, no infrastructure, it is station to station. It's used, for instance, in VANET, vehicular ad hoc networks. In managed or infrastructure mode, you rely on access points to relay transmissions and synchronize communications between the mobile devices in Wi-Fi and with the wired network which goes to the core network. In mesh mode, you have an infrastructure with multi-hop on radio links between several access points and until you finally reach the wired network if it exists. So in ad hoc mode, you see here the principle. You have two devices. They have a direct connection through the Wi-Fi standard. In managed mode, you have an access point, so he manages both mobile devices, so even if they are communicating with each other, they go through the access point. And if they want to reach farther, they go through the access points to a remote network. In a mesh network, you have here the core wired network with an internet access. It's not mandatory, but usually it's like this. Then you have a first access point which bridges between wired and wireless network, and several hops through other access points through virtual radio links, which are routed through all the mesh network. So when we want to get the Rssi information and all that's relevant for the positioning system, we need to filter the proper fields and packets. So first, the 4 addresses fields carry different values given the combined values of to DS and from DS flags. So first, if to distribution system is 0 and from distribution system is 0, it means that you are in ad hoc mode. So first address is the destination address, second address is the source address, and the last address is the BSS ID. Address 4 is not used. With 2DS0 from DS1, you are sending a packet from the access point to one of its mobile client. So the first address is the destination address, the second is the BSS ID, the third is the source address. So this one is the access point MAC address, and this one is the mobile station MAC address. With 2 DS1 and from DS0, you are sending a packet from a mobile device to the access point. First address is the BSS ID, then second address is the mobile device address, and the third address is the destination address, which is the access point address. With both flags to 1, you are in a mesh network. So here you have the first address, which is the router address. This one, the relay address, which is the next hop. Here the transmitter address, which is the source access point. Here the real destination address of a mobile device, and this the real source address of a mobile device.